Welcome all staff, faculty, midshipmen, and alumni. I'm a midshipman first class Willis, and I worked on the software components of this project.
I am first class Mitchell Luckinbill, and I worked on the electrical components of the project.
And I am midshipman first class Thomas Larrea, and I worked on the mechanical part of the project.
Mr. Larrea, could you give us a quick intro into what was your team's goal?
Our team was tasked with the problem of completing a working base design for the robot football team that complied with all of the league's regulations. We also were tasked with building 8 robots after the completion of a working prototype. The base was required to be modular and able to easily integrate with all of the other subgroups' designs. The previous year's teams had a mostly working base, and we were expected to build off their design to meet the regulations, create a modular base, and improve the robustness of the robot in order to ensure playability. In addition, we decided to tackle the issues of a more intuitive controller software integration and installing an omnidirectional wheel rather than the 2 caster wheels used by the previous team. Finally, we decided to tackle many other small design improvements in order to make the robot more effective during competition. Here's a quick look at last year's base.
Mr. Willis, can you tell us what last year's team handed over to you?
To reiterate what first class Larrea was saying, last year's robot was built and was functional. It was actually able to compete in the combine portion of last year's tournament. Unfortunately, they were not able to have a full team built and be able to participate in last year's actual game.
Mr. Luckinbill, what was your team's plan to get the robot to be game ready?
To make our robot completely game ready, we needed to meet all of the rules and regulations of the Robot Football League, such as include a bumper around the robot, have completely 360 visible lights, and install the tackle sensor, which is easily accessible within 10 seconds of the referee needing to reset the robot. We also decided to get a new front wheel with a 3D printed file that connects the wheel to the base. We decided to improve upon the previously coded Xbox controller. We decided to lower the battery to drop the center of mass and make it stronger in game. And we decided to remove the extra battery pack and make the base completely modular and compatible with other teams. Finally, we needed to build 8 robots in order to field the team successfully.
As a team, what were you all able to accomplish?
On the hardware side, we had new cutouts to maximize the internal space of the bot while still meeting the size requirements to include the rubber bumper. We added an omnidirectional wheel, which is a ball transfer unit, and it was attached to the bot via a 3D printed mount. We also cut out an area and built a platform to hold a lowered battery, giving us a lower center of gravity and better stability. We found better locations and mounts for all of the internal pieces, added 1/4-inch walls, and blue wheels for better traction. We also dove deep into the gearbox and powertrain that the previous team used and found a lot of potential issues in parts that we would have to fabricate ourselves or get the machine shop to fabricate for us.
On the software side of things, the programming language C++ was the language that was used and read by the Raspberry Pi. We used the Raspberry Pi connected to Thomas's, as he mentioned, the Kangaroo to send commands and drive the motors. The Raspberry Pi was also wirelessly hooked up to an Xbox controller, which is how a user would send commands to the Raspberry Pi to be able to essentially control the robot. The code was pretty simple. We had gains and we had speed and turn equations. And these equations, along with the gains, is what allowed us to control how much signal input was being pushed to the Raspberry Pi, and then essentially transferred and read over to the Kangaroo, allowing the Kangaroo to do its job. The Xbox controller is the most essential part in a sense of we want to use the Xbox controller to comfortably be able to control the robot. The robot, the Raspberry Pi reads numbers in between negative 32,000 and positive 32,000. These signals are sent to the Raspberry Pi from the Xbox controller, but those are not the same numbers that are sent from the Raspberry Pi to the Kangaroo. So learning how to overcome this obstacle and finding the right gains and equations to be able to get what you want from the Xbox controller and also have the robot understand that. A lot of that was done in the code, reprogramming speed equations, turn equations, trying to find the right gains. There was a huge difference. There could be a huge difference in rather if the sign was negative or positive to how the robot will react to you trying to turn left, trying to turn right, or trying to go straight. Moving forward, we used last year's team. They used one joystick to control the robot as they thought this was the best technique, or they thought, this was a way that they could get the job done. Either way, we went more of mapping out the Xbox controller to be of something of what you would see during a video game. Most people our age are used to playing video games where right trigger will be forward, left triggers go backwards, and you use one joystick to turn left or right. And even furthermore, you might have, X or Y be a brake button. And so we really thought for the best control and competition that reprogramming the robot to this format would allow us users to be better controllers of the robots.
So the electrical components of the robot, we were able to institute the tackle sensor, which has a 6-pin DIN connector that attaches to the LED lights. So in order to set up that integration, what we found was the easiest was to get a 6-pin DIN cable and cut it in half or a couple inches from one of the ends of the connectors and plug that into the tackle sensor, and then hard solder each of the individual wires for each of the 6 pins to the LED light strip. And that was an easy way to integrate it, and a very cheap and effective method. We also added in an electrical bus to the robot to be able to clean up the wiring system, as well as connect and integrate with any other of the teams that need to put on their components to our base. Finally, we decided that if we could, we would like to get rid of that extra battery pack that the previous year's team used to power the Raspberry Pi in order to maintain a positive 5 volts at all time. So we took a 5-volt, a fairly small and cheap 5-volt regulator, and used that to attach to the Raspberry Pi, and that replaced the whole battery pack that the other team used.
Now here are some photos and a quick video of our final designed robot.
All right.
Good work, gentlemen. I've never been so proud. All right, cool, we're done.
Wonderful. Now, Mr. Larrea, if you could give next year's robot football team a list of things to do, what would it be?
We believe that next year's team should finish up the cable management and the bus wiring for all of the components to allow easy access for all of the other sub-teams. Order and have the shop complete all of the parts required for the 4 bots, as we have most of those parts identified. completing all 4 walls and furnishing a top for the bot, and finding new ways to mend the code for smooth control over the robot. And finally, that all leads into integration with the other robotic subteams.
We really look forward to what next year's team has to offer. Good luck to everyone who is furthering on our legacy. I wanted to take the time to thank everyone for listening. Again, my name is Midshipman First Class Willis.
I'm First Class Larrea.
I'm First Class Luckinbill.
Thanks again. Everyone have a good one. Are we going to cut that?